Alright, let's continue. Okay, let me open the table of content first. Alright. Okay. We are in chapter 21 and still on homework measurement here. Let me open that. Basically trying to understand the swiping mechanism with this VMstat tool, I guess, and the mem program or something like that. Okay. Yeah, I tried this out on off stream, I guess, and I'm still not sure how to make sense the number. Yeah, sometimes what is it called? The SO here, the swap out, I guess, is larger than the swap in. How can that happen? I'm still not sure. But yeah, you can try this out yourself. I don't think I will try this on stream because I might get the out of memory error, something like that. Okay, let's take a look at this. Question 4. Do the same experiment as above, but now what's the other statistic? Okay. How do they change when mem is running? Alright, I guess I will do this off stream too. Again, I don't really want the live stream to be cut off because of out of memory, because I'm running out of memory. Okay, now let's examine performance. Pick an input for mem that comfortably fits in memory. Say 4000 if the amount of memory on the system is a gigabyte. Okay. How long does loop 1 take? And subsequent loops 1, 2, etc. Hello, study in Git, I guess. What year you in? And in that year, just did physical memory, mostly fragmentation and paging. I'm not in any year, I guess. I'm learning this just for fun, you know. So yeah, I'm not in university or something like that. Okay, now pick a size comfortable beyond the size of memory. Says 20,000 again, assuming a gigabyte of memory. Oh, okay. How long does loop 0 take? And subsequent loops 1, 2, etc. Now pick a size comfortably beyond the size of memory. How can the size be comfortable if it is beyond the size of memory? Can assuming a gigabyte of memory. How long do the loops take here? How do the bandwidth numbers compare? How different is performance when constantly swiping versus fitting everything comfortably in memory? Can you make a graph with the size of memory used by mem on the x-axis and the bandwidth of accessing said memory on the y-axis? Finally, how does the performance of the first loop compare to that of sequence loop? For both the case where everything fits in memory and where it doesn't. Okay. If I remember correctly, the zero loop or the first loop here will take longer than the subsequent loop. But well, let's find out, I guess. Okay, what is it again? Okay. VM beyond physics. Okay. Let's just 8000, I guess. I have 16 gigabyte of memory, if let's say we have 8, then we use 4000 here. So let's use 8000 VM start. Okay, and then 1 second. If I remember correctly, yeah, this one. Delay and count. Okay, let's put the count 10 or 10 report or something like that. Okay, and this. Okay. See, getting the loop 0 might be longer than the subsequent loop. Okay. Now let's take a look at the performance. Alright. How long does loop 0 take? Yeah, from this information, it looks like the loop 0 is significantly longer than the loop 1, 2, and 3, and so on. Okay, that's quite interesting. How long do the loops take here? How do the bandwidth numbers compare? Okay, for the beyond the memory size here, I guess I will try that out off stream, not during this live stream. Again, I don't really want to get out of memory situation. Okay. How does the performance of first loop compare to that of sequence loop? Okay. At least for this, for the first case, where the input for mem program fits in memory, right? The first loop is significantly take longer time than the loops, the subsequent loop, like loop 1, 2, 3, and so on. And I'm kind of curious about what is it called? The CPU usage, maybe. Okay, this is the user time. Alright, I assume this is when we run the mem program, because usually when we run the mem program, the CPU usage time spike up, usually, or maybe starting from this, maybe from this, okay. Yeah, there is two possibility. And you know what, why don't we try that again? Okay, right, we are in this. Okay, alright. Okay, this is the CPU usage, right? And then the free memory inactive. Okay, there's not much change in the inactive information, I guess, but the active is, I guess, increase significantly. Okay. Alright. Yeah, maybe let's try this one. Okay. I assume this is when we, this is the last, maybe the last mem execute, and after that, yeah, we are not running mem again. Maybe. Okay, let's take a look at the memory here. Okay, this is the free or idle, I guess, the memory. I assume this is before we start the what is it called? The mem program. And this is when we start the mem program. Maybe the loop 0. And after this the subsequent loop. Maybe something like that. Oh, and then this one is starting to terminate the, what is it called? The mem program. The idle memory increase here. Okay, interesting. And the inactive information didn't really change that much. Alright. Okay. But the active information here, yeah, jump quite a bit. Okay, so I assume, I'm not sure if this is correct, but I assume this is when we start the mem program. Yeah, let's try again. Okay, or maybe this one, starting the main program, loop 0, and then okay. Yeah, maybe this is when the loop 0 starting, and then the loop 1, and so on, maybe, until I terminate during this time. Okay. Yeah, I'm looking at the idle memory here. The change in idle memory to, I guess, trying to understand when the program start and terminate. Okay, that is quite interesting. Yeah, I'm not sure about the performance here. Yeah, I need to try this off stream later on. Okay, or well, maybe you can try this yourself. Let's check the question 6. Swap space isn't infinite. You can use the tool swap on with the -s flag to see how much swap space is available. What happens if you try to run mem with increasingly large values beyond what seems to be available in swap? At what point does the memory allocation fail? Right. I mean, I assume if the memory allocation fail, we will have out of memory situation. Maybe. I'm not really sure about that. But yeah. And I'm kind of curious, what happened if we didn't have swap space, you know? Like, let's say we have 8 GB of memory, but we allocate 12,000 here, or maybe around 12 GB without the swap space. Will we have the out of memory situation? I'm not sure. Okay, this look like something dangerous to try on stream. Again, we are checking the point of failure here, which means the live stream may cut off absurdly. Okay. Finally, if you are advanced, you can configure your system to use different swap device using swap on and swap off. Read the main page for the tile. If you have access to different hardware, see how the performance of swapping changes when swapping to a classic hard drive, a flash-based SSD, the solid-state drive, and even a RAID array. I'm not sure about this one. Okay, how much can swapping performance be improved via newer device? How close can you get to in-memory performance? Yeah, I think we can have the swap space on different configuration, if I remember correctly. there any? Okay. There are two main pages here, manual page. What is the egg one? Oh, util Linux, okay. And I guess the second one also Linux, okay. This is the system call. Oh, okay, right. I think we want to check this one. The CLI maybe. Okay. Yeah, if I remember correctly, this is how I set up the swap partition on my device. Yeah, I kind of forgot. Swap partition. Yeah, maybe this one. Swap on the tissue. Maybe the test S here is equivalent to show. Maybe. Oh no. This is the summary, I guess. This output format is deprecated in favor of show. That provides better control on output data. Okay, so instead of using this as like this question information, we can use this show instead, because well, it is deprecated, right? And we have no idea when it will be removed entirely. Display a definable table of swap areas for a list of available columns. Okay. Let me check. Okay. Yeah, this is the information, I guess. I have NVMe here. And my swap is 24 gigabyte. I'm not sure if that is too big or not, but yeah, I read somewhere that at least maybe around twice the what is it called, the actual memory or something like that. But yeah, I'm not really understand what's the right amount of swap space will be used, or should I use maybe something like that. So I tried 24 gigabyte and so far haven't really used it that much. Okay. Yeah, for this one, I don't really have any access to different hardware here. Okay, well, maybe just skip this one, I guess. Alright, let's continue to Chapter 2020, Beyond Physical Memory Policies. Okay. is recently used, if I remember correctly. Yeah, let me open that. Swapping policies. Beyond physical memory policies, in a virtual memory manager, life is easy when you have a lot of free memory. Life is easy. Okay. In a virtual memory manager, life is easy when you have a lot of free memory. A page fault occurs, you find a free page on the free page list and assign it to the faulting page. Yeah. Okay. Again, when we have a lot of free memory, right? When a page fault occurs, we find free page on the free page list and assign it to the faulting page. Hey operating system, congratulations, you did it again. Unfortunately, things get a little more interesting when little memory is free, right? In such a case, this memory pressure forces the operating system to start patching out page to make room for actively used page. Deciding which page or pages to evict is encapsulated within the replacement policy, right, of the operating system. Historically, it was one of the most important decisions the early virtual memory system made, as older systems had little physical memory. Minimally, it is an interesting set of policies worth knowing a little more about, and thus our problem. Okay. Older system had little physical memory. Okay. And the problem here, the crux of the problem, how to decide which page to evict. How can the operating system decide which page or pages to evict from memory? How can the operating system decide which page or pages to evict from memory? This decision is made by the replacement policy of the system, which usually follows some general principles discussed below, but also includes certain tweaks to avoid corner case behavior. Okay. Yeah, I'm kind of curious about the replacement policy here. How do we decide to, I guess, free the page from memory, or maybe put that in the swap space if we have the swap space. Okay, case management. Before diving into policies, we first describe the problem we are trying to solve in more detail. Given that main memory holds some subset of all the pages in the system, it can rightly be viewed as a cache for virtual memory pages in the system. Okay, before diving into policy, describe the problem we are trying to solve in more detail. Given that main memory holds some subset of all the bits in the system, it can rightly be viewed as a cache for virtual memory bits in the system. Thus, our goal in picking a replacement policy for this case is to minimize the number of cache miss. In picking a replacement policy for this case is to minimize the number of cache miss, that is, to minimize the number of times that we have to fetch a page from this. Alternately, one can view our goal as maximizing the number of cache hits, that is, the number of times a page that is accessed is found in memory. Okay, minimize the number of times we have to fetch a page from this. Yeah, I'm kind of curious what happened if we didn't have the swipe space, Is the page just gonna be free? And we need to and we don't need to fetch the page from this. Yeah, I'm still not sure. I mean, so far we have we assume we have the space, the swap space, if I understand correctly, from this one, right? So what happens when we don't have swap space? Okay, alternately, one can view our goal as maximizing the number of cache hits, the number of time a page that is accessed is found in memory, right? So we are trying to maximize the number of time the page found in the memory instead of this. Okay, knowing the number of cache hits and miss, let us calculate the average memory access time, AMAT. Oh, average memory access time. For a program, a metric computer architect compute for hardware cache. Oh, there's a metric. Okay. A metric computer architect compute for hardware cache. Specifically, given this value, we can compute the AMAT of a program as follows. Okay, average memory access time here. What is the M? And this one. Is this the time access memory? Maybe. Okay, where the M represents the cost of accessing memory. Oh, okay. The cost of accessing memory. Maybe the time needed for accessing memory, something like that. And then TT, the cost of accessing this, the time needed to access this, maybe we miss, okay, the probability of not finding the data in the case. Oh, this probability, okay. What is it again? Average memory access time. Average memory access time. PMIS varies from 0.0 to 1.0, and sometimes we refer to a percent miss rate instead of a probability. For example, a 10% miss rate means PMIS equals 0.10. Oh, we refer to a percent miss rate instead of a probability. Note, you always pay the cost of accessing the data in memory. When you miss, however, you must additionally pay the cost of fetching the data from disk. Oh, okay. Alright, so we always trying to access the data in memory, right? That's why this will always have a value, I guess, something like that. Regardless we miss or not, right? But when we miss, we have another cost here. Okay. Again, we always pay the cost of accessing the data in memory, like checking if the data is in memory or not. If it is in memory, then we don't have the case miss. But if it is not in the memory, then, well, we have another cost for fetching the data from this. Okay, for example, let us imagine a machine with a tiny address space, 4 kilobyte with 256 byte page. Thus, a virtual address has two components, a 4-bit virtual page number, the most significant bits, and an 8-bit offset. Okay, this is the page size, right? So that's why we have the 8-bit offset here. So maybe something like this. At 256, so each page have 256 byte, maybe something like that. Contains 256 byte, a significant bit. Thus, a process in this example can access to power 4 or 16 total virtual pages. 16 virtual pages here from this one. Okay. Right, we have this 4 kilobyte or maybe kbbyte, I guess. And well, maybe something like this. We have 16 virtual pages, right? And then is it something like this? Okay. And then 16 is 2 power 4. So we have 4-bit virtual page number here. just a little bit of refresh from the previous chapter. Okay, thus a process in this example can access 16 virtual pages. In this example, the process generates the following memory reference. That is virtual address. Okay, this one. Oh, interesting. The following memory reference. This virtual address refer to the first byte of each of the first 10 bits of the address space. The page number being the first hex digit of each virtual address. Memory reference. Okay, so we have, I guess, 10 memory reference or virtual address. This virtual address refers to the first byte. Okay, the first byte of each of the first 10 bits of the address space. The page number being the first hex digit of each virtual address. The page number being the first hex digit of each virtual address. Okay, if we take a look at what is it? I guess chapter 20, the multi-level page table example. Oh no, not that one. Okay. What is it called? Chapter 20 info. Where is it? Yeah, maybe this one. We have some kind of, what is it called? Some kind of multi-byte, I guess. So the first hex digit is maybe something like this, 7F, and this is the second hex digit. So imagine that this page number we can get from this hex digit or the first byte from the virtual address, maybe something like that. Okay. You might as well have a digital whiteboard and draw what you understood from the basics. Well, maybe later on. But I honestly prefer to just type it out, rather than drawing. Like for example this one. I prefer this kind of representation rather than drawing, because it is easier for me, I guess, but some people might prefer drawing stuff. So yeah, it's just personal preference. But I will consider that for the future, but no guarantee. Alright. Hello Luigi, yo, how are you, bro? Well, I'm still alive, I guess. Do you use a linter? It depends. Wait. Yeah, it depends. If the linter is good, then I will use the linter. If it is not, then no, I guess. Again, sometimes the linter might be finicky or something like that. So I just turn off the linter. So yeah, it depends. Let us further assume that every page except virtual page 3. Let us further assume that every page except virtual page 3 is already in memory. Okay, every page except virtual page 3 is already in memory. Thus, our sequence of memory reference will encounter the following behavior. Okay. Every page except virtual page 3 is already in memory. Okay. So I assume we have 10 pages here. Okay, maybe something like this. I don't know if I can copy this. Okay, looks like I can. How do I split this? Maybe something like this. Oh no, okay. Yeah, well, let's just use macro, I guess. Alright, we have this, then okay, we hit every page except virtual page 3. Okay, except virtual page 3, I assume maybe this one. Again, I'm not sure the starting point here. Are we starting from 0 or from 1? If this is virtual page 0, then this might be the virtual page 3. But if we consider this as virtual page 1, this might be the virtual page 3. So yeah, what is the starting point here? I'm not sure. I assume, well, let's just assume from 1, I guess. Virtual page 0, right? Virtual page 1, and then virtual page 2. Okay, and then this one, virtual page 3. So yeah, let's start from 0. Okay, this is the virtual page 3, and well, we miss. Okay, hit, miss. It looks like we start from 0, virtual page 0. Okay, miss. We're missing in this one. We can compute the hit rate, the percent of reference found in memory, 90%, as 9 out of 10 reference are in memory. We can compute the hit rate, okay, the percent of reference found in memory, 90%, as 9 out of 10 reference are in memory. Okay, the miss rate is thus 10%. So the p miss here is 0.1. In general, p hit plus p miss equal 1.0. Okay, hit rate plus miss rate sum to 100%. Okay, so p hit, that sounds weird, and p miss 1.0. Something to keep in mind. So the p miss is 10%. Calculate the average memory. What is it again? Average memory access time. Okay, the access time. Alright, where is it? To calculate the average memory access time. Okay, the access time here. We need to know the cost of accessing memory and the cost of accessing disk, right? How much time needed to access the memory and accessing the disk? Maybe something like this. Assuming the cost of accessing memory, the TM is around 100 nanosecond, right? And the cost of accessing disk is 10 millisecond. Oh, okay. This one is nanosecond and this one is millisecond. I assume we need to, what is it called? Normalize this, or make sure this is in the similar measurement. Okay, we have the following average memory access time, 100 nanosecond plus, okay, 0.1 multiply 10 millisecond. It is 100 nanosecond, okay, plus 1 millisecond. Okay, right. Or about 1 millisecond. Interesting. Okay, if our hit rate had instead been 99.9%, p miss equal 0.001. The result is quite different. Average memory access time is 10.1 microsecond, or roughly 100 times faster. As the hit rate approaches 100%, average memory access time approaches 100 nanosecond. Okay. Unfortunately, as you can see in this example, the cost of this access is so high in modern systems that even a tiny miss rate will quickly dominate the overall average memory access time of running program. Is so high. Okay. In modern systems that even a tiny miss rate will quickly dominate overall average memory access time of running program. Clearly, we need to avoid as many miss as possible or run slowly. Run slowly at the rate of the disk. We need to avoid many miss as possibly or run slowly. of the this. One way to help with this is to carefully develop a smart policy as we do now. Okay, run slowly at the rate of the this. At the rate of the this, I mean. Okay. Tiny misread. Alright. The optimal replacement policy. Okay. Hello, Sen. Don't have time to stay to invite. Okay. I'll see you next time, I guess. Okay, the optimal replacement policy. Alright. I guess I will continue this on the next session. Yeah, to better understand this more, I guess. I need to teach this first, like the average memory access time. Okay, let's continue this on the next session. So I guess that's it for now. Thank you for watching and see you next time. Bye bye.